Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 8-7 homework solutions on binomial distributions. For this problem, they're saying let x equal the number on a tennis ball randomly chosen from a bag that contains 5 balls with the number 1, 3 balls with the number 2, and 2 balls labeled 3. We just want to make a table and draw a histogram showing our probability distribution for x. So our table, we're going to have the label, we're going to have the frequency, and we're going to have the probability. So our labels are going to be 1, 2, and 3. That'll be our x, our input for our random variable. And then the frequency of each of those, they said that there was 5 of those 1s. We had 3 of the 2s and 2 of the 3s, because that's not confusing. And then for the probability, well, these all add up to 10 total tennis balls. So the probability of each, for the 1s we have 5 out of 10, or 1/2. For the 2s we have 3 out of 10. And for the 3s here we have 2 out of 10, which we can reduce to 1/5. Let's go ahead and graph these now. Horizontally, my 3 values are just going to be 1, 2, and 3. Pretty simple. Vertically, the highest we go is 1/2. And these are kind of going by tenths. So I'll just do 0.1 through 0.6 for my vertical grid lines here. All right, so for my 1s, that goes up to 1/2 or 0.5, so right up to here. For the 2s, that's going to go up to 3/10 or 0.3. And for the 3s, that's going up to 1/5 or 0.2 right here. For this problem, they're saying let n equal the number of digits in a random integer from 0 to 999. They want us to make a table and draw a histogram showing our probability distribution for n. So let me start by making a table. My first row is just going to have the possible values for n. The next one's going to have the frequency for those, and then we're going to have the probability for my last row. So for my possible values for this random variable, the number of digits that I could have in one of these numbers is either going to be 1, 2, or 3. The frequency of those, so from 0 to 9, those are all of our 1-digit numbers, so there's 10 of those. And then from 10 through 99, those are all of the 2-digit numbers, so there's going to be another 90 of those. And then from 100 through 999, that's going to be a total of 900 of those 3-digit numbers. For the probability, we need the total of these. Well, from 0 to 999, that's literally 1,000 numbers, so that's pretty easy to work with. So now we've got, for our probabilities, a 1-digit number. That's going to be 10 over 1,000. So we could do 1 over 100, or 0.001 if we want to make a decimal. And then for 90 over 1,000, that's going to be 0.09. And then 90 over 1,000, or 900 rather, over 1,000 is going to be even easier. That's going to be 0.9. So for our histogram, we've only got 3 values horizontally, 1, 2, and 3. And now for the vertical, if we make these go by like 0.2s or even 0.1s, if you don't mind more grid lines, any of that will make it easy to see what's going on here. So the 1s went up to 0.01. That would be like, I don't know, 1. So this is 0.20 essentially. So this would be like 1/20th of a grid line. It's pretty low, hard to see. And then for 2s, we're going up to 0.09. So that's almost 0.1. So almost halfway up that first grid line. And then for 3s, we're doing 0.9. So that is halfway between 0.8 and 1.0. So there's our histogram. For the next couple of questions, we're using the probability distribution given in this histogram. What happened here was, I think they spun a spinner, and these are the number on the spinner and the number of times the probability of actually spinning those. So one thing we can kind of see right away, since these are not even results, is probably that this spinner does not have even areas unless this is kind of a map of the trials that happened. So first question they have is, what is the number that is most likely to be spun on the spinner? Well, we just have to look for the highest probability. 2 has the highest bar here, so let's go with 2. Now, what is the probability of spinning an even number? Now we need to look at the probability of our even numbers here, 2 and 4, and add those probabilities together. The probability of 2, well, what are my grid lines going by? It looks like we're going by 1/8, right? Because it takes 2 of them to get to 1/4. So this right here looks like 3/8, and the probability of a 4 is going to be 1/4 or 2/8 if we want the same denominator. And that's going to give us a grand total of 5/8. For this problem, they want to know the probability of flipping a coin 20 times and getting exactly one head. So this is one of those binomial experiment sort of situations. We've got n independent trials. We've got 2 outcomes, success or failure, which in this case means heads or tails. And we've got the same probability each time we flip these. This means that we can use our binomial probability formula. So we're going to have n choose k. In this case, the total number of trials, 20. Choose the total number of successes, 1. So n 20 choose 1. And then the probability of success is heads, so that's going to be 0.5 raised to the number of successes, which in this case is 1. Probability of failure is the probability of tails, which is also 0.5. And the number of failures is 20 minus 1, or 19. And then we just plug this into the calculator. So plugging this in, let me do my 20 choose 1 first. That's n capital CR, parentheses 20 comma 1, times 0.5, and you can raise it to the first or not, doesn't really matter. And then 0.5 raised to the 19th, that matters. And it comes out to this crazy number here. So we will round this off to 1.907 times 10 to the negative 5. That is our probability, a very low probability of getting exactly one head. For this one, they want us to find the probability of rolling a 1 exactly 3 times in 5 rolls of a 6-sided die. This is one of those binomial probability experiments. We've got n independent trials. Each dice roll is independent of the others. We've got 2 outcomes, success, which in this case means rolling a 1, and failure, which is rolling anything other than a 1. And we have the same probability of successes and failures each time. So we can use our probability binomial formula. So that's going to be n choose k times success to the k and failure to the 1 minus, or the n minus k. So plugging things in specifically, we've got 5 choose 3. We want 3 successes. And probability of success in this case is, we just want this 1 here, so that's 1 out of 6 for that possibility. And we want 3 successes, so 1/6 to the 3rd power is this next piece. Now we need the failures to the probability of failure to the number of failures. So if 1/6 is success, then 1 minus that, or 5/6, is failure. And then we need 5 minus 3, or 2, for the number of failures. So let's plug all this in. So on the calculator, let's do NCR, parentheses, we want 5 choose 3, so 5 comma 3. And now let me do parentheses, 1 divided by 6, close parentheses, raise that to the 3rd. And now we also need parentheses 5 divided by 6, close that and raise that to the 2nd power. And that gives us 0.032. So there's about a 3.2% chance that we get a 1 exactly 3 out of the 5 times. So pretty unlikely. For this problem, in our school, they're saying 30% of students plan to attend a movie night. You randomly ask 5 chosen students from your school whether they plan to attend the movie night. We want to do a few questions based off of this. First, they want a histogram of the binomial distribution for the survey. Then they want to know the most likely outcome and the probability that at most 2 students plan to attend. All right, let's start with that binomial distribution. For that, we will use a modified version of the binomial probability formula. So we're going to modify it so that we can plug in whatever we want for the number of successes. Normally, it would be n choose k times p to the k and 1 minus p to the n minus k. We'll just replace all those k's with x's and put in a few parameters as well that match it up with this problem. So in this case, instead of doing n choose k, we're going to do 5 choose x. That allows us to plug in as many successes as we want. And now for the probability of success, that's our p-value. They said 30% plan to attend, so that would be 0.3. And we're going to raise that to the number of successes, which is x. So 0.3 to the x power, that's the p to the k part of this. And now the 1 minus p to the n minus k part, the probability of failure. If we have a 30% chance of them saying yes, then there's a 70% chance that they say no, so 0.7. And we're going to raise that to the 5 minus x. That'll give us the number of failures in each case. So let me set up a table here. And we're asking 5 students, so there's 6 possibilities that we could get. We could get none of them say yes, 5 of them say yes, and anything in between. So 0 through 5 are going to be the values of our random variable that we're plugging in to this formula here. Now let's actually enter this formula in Desmos and calculate all these values. So here I am in Desmos. Let me write my formula. P of x equals, and now to do the 5 choose x, I'm going to have to do NCR, parentheses 5 comma x, and that does the same thing. And then we have 0.3, raise that to the x, and then 0.7, and we're raising that. And I need a parentheses for this because I've got multiple things going on. So we're going to do 5 minus x up there. Now let me go down here and plug in the numbers 0 through 5. So we got p of 0, first of all. That's 0.168. Next, let's plug in 1. That gives us 0.360. Now let's do 2. That's giving us 0.309. Next we have 3. That gives us 0.132. Now we do 4. That's going to be 0.028. And finally, plugging 5 into there. All 5 students saying yes. There is a 0.002% chance that that happens. So not very likely. Now that we've got all this filled out, let's make our histogram based off of all this. So for my horizontal values, I've got 6 of them, 0 through 5. And then vertically, the highest percentage I have here, or the highest probability, is this 0.360. So I need to make my grid lines at least go up to that. So what I'm going to do to accomplish this is I'm going to do my 0 through 5 down there. That's the number of students. And then for the probability, I'm going to go by 0.05s, and I'm going to go a little bit above 0.35. So that'll let me get that 0.356, or 0.36 here. Let's go and graph all these now. So 0.168, that's somewhere in this area right here. That's for the zeros. For the ones, this was the highest one, going up to 0.36. That's like as high as I can go on this. And then for 2, 0.309, that's like 0.31, which is about here. And then for 3, we have a big drop off. This is 0.132, so somewhere down here. And then for 4, we have 0.028, that's like 0.03. That's somewhere halfway between that. And then we've got 0.002, which is practically 0 for our purposes. We'll just put a little kind of honorary bar there. And there is our histogram. So now they want us to answer a couple questions based off this. What's the most likely outcome of your survey? Well, that's pretty easy to see from the histogram. 1 has the highest bar, so it's most likely that 1 student plans to attend, which is kind of sad, but hey, it is what it is. So now, what's the probability that at most 2 students plan to attend? Well, we need to take the probabilities of 0, 1, and 2 and add them together to get at most 2. So we got these 3 decimals being added, and I'll go to the calculator for that. So we've got 0.168 plus 0.360 plus 0.309, and that comes out to 0.837. So there's an 83.7% chance that no more than 2 people are going to show up to this movie night.